Welcome to this video. Here we are going to discuss about structure of page table. Here what is paging? It's a memory management technique to translate the logical address into physical address. Here the physical address space of process can be non-continuous. This process can be allocated physical memory whenever the later is available. It avoids external fragmentation. Then the physical memory, the fixed size of blocks in physical memory is called frames. In logical memory it's called pages. Here we need a page table to translate logical into physical address. Example, this is the address. The CPU can generate this page number P and offset D. Here this page number is indexed into the page table, the page number. Totally we have m bits in the address, then n bits for displacement and m minus n for this page number P. Here the logical address space 2 power m and page size is 2 power n. Here this is a hardware for translating logical address into physical address. The CPU generates the logical address which consists of page number P and D displacement. The displacement will be taken as it is in the physical address. Then here P gives the information about where the frame is available, the frame number. Then take the frame number as a P. Then the physical address is generated. Find that location to access the content in the main memory. Then here for example there are 4 pages page 0, 1, 2, 3. There are 4 pages. Here how do you find the physical address? C0 in page table, it is available in that first frame. Then second, page 1 is available in the fourth frame. So go to the fourth frame for finding that page with content. Okay, each block assuming there are 4 bytes. Then here you have to go for multiplying each number with 4. So what about this is page number 0? The page number 0 refer the frame number. The frame number of this one is 0. It is 5. So 5 into 4 it's available in the 20 because each block you have 4 bytes. Then the page number 1, refer where the page number 1 is available. It is page number 1, it's in 6th frame. So how do you reach the 6th frame? 6 into 4, 24. This is the way we can access the content. Convert this logical address into physical address. Then the calculating internal fragmentation. Internal fragmentation in the sense we are going to allocate the memory. Okay, this is a memory. Here it needs one, it's a size of this block is 10. Then we need 2 blocks of memory for loading data. So it's occupying 2 MB, but there are the size is total size is 10 MB, but the remaining thing is wasted. This leads to internal fragmentation. So the process page size is 2048 bytes, then process size is 72,766. So we need 35 pages plus one extra 1086 bytes we need. But each is occupying 2048. Then you are going to allocate this for this last one, 36th page. Then the remaining 962 bytes are wasted. Okay, that is not occupied. So we are wasting this one. So this is called internal fragmentation. Here, free frames. How do you maintain the free frames? Then how do you load the page in this into free frames? Here, before allocating that, here the list will be maintained like free frame list. The free frame list you have 14, 13, 20. These are all the free frames available in main memory. Here we have a new process available in the disk secondary storage. Then how do you allocate the 0, 1, 2, 3? Okay, this is before allocation. So here after allocation, find 0. Okay, find 0. 0 will be placed in, see, 0 will be placed in that 14 or something. Okay, 14. Here they are allocating 0 in 14. So how do you maintain? 0 is available in 14. The page table is having that information. Then you are allocating the 1 in 13. So that should be represented in that page table after allocating. Now the free space is also removed. 13, 14 are removed. So the free frame list only 15 is here. After allocating 0, 1, 2, 3. Now what about 2? 2 is placed in here. 2 is 1 is in this 13 and 2 is in 18 and 3 is in 20. So after allocating, the page table maintains the information where it has been allocated. Then the free frame list is only 15 is available after allocation. Then how do you implement this page table? Okay, page table is kept in the main memory. Here we have the PTBR and PTLR. Page table base register that points to the page table, and page table length register indicates the size of the page table. So this scheme, every data and instruction access requires two memory accesses, one for the page table and one for the data or instructions. Then two memory access problem can be solved by the use of a special fast lookup hardware called associate memory or translation look-aside buffer TLB. Then some TLB stored address space identifiers like ASID in each TLB entry. Okay, it uniquely identifies each process to provide address space protection for that processes. So TLB typically small when compared to page table. It is 64 to 1024 entries. If TLB miss, the value is loaded into the TLB for faster access next time. Then the replacement policies are considered for this loading that fast access, loading this data into TLB. Some entries can be wired down for permanent access. Then associate memory. Associate memory is a parallel search. Here we have the page and the frame information. The address translation consists of page number and displacement. P is in the associate register, get frame out. Otherwise get frame from the page table. Here paging hardware with TLB translation look-aside buffer. Actually, instead of searching that directly in main memory, you can have a small buffer called TLB. Actually, page table is kept in the main memory. So here we have a like cache, we have a small TLB in between this. So here we are going to find that this is a logical address with page number and displacement. First, we are in directly we are going to that, instead of going to that page table, search this in TLB, translation look-aside buffer, where's that page number, get the corresponding frame number. Add to that if hit occurs, hit in the sense that frame number is available in the TLB. Then get this displacement value as it is and get the physical address. Okay, this is a one way. If the TLB miss occurs, TLB miss in the sense you are trying to search the frame number of the given page number, it's not available. Then you should go to that. If miss occurs, TLB miss occurs, go to the page table and find the frame number, add it to that physical address displacement to generate the physical address. So there are, so here like cache, we have a TLB between CPU and the page table. If the page number is available, it's having maximum of 1024 entries. Here if the page number of the particular frame number is available, then access and generate the physical address. Otherwise, if TLB miss occurs, go to the page table and find the frame number. It's for fast access. Then effective access time. Okay, here this can be hit occurs, then the effective access time will be calculated like if lookup is there in eta, alpha, this formula is used for calculating that effective access time. Then memory protection. How do you protect the memory? Memory protection implemented by associating the protection bit with each frame to indicate if the read only or read write access. The particular frame is for read only or read write. Then we have a bit called valid or invalid bit. Okay, entry in the page table. So valid bit indicates that page is logical address space and thus it's a legal page. Invalid indicates that the page is not in the process. Okay, so it's going to, so the logical address we have, it's an invalid one. So the use page table length register PTLR is used. If any violation comes, then give the error, traps it to the kernel. Here valid or invalid bit, this is the page table. Each page table you have a page number, then corresponding frame number is stored in that, then it's a valid or not. For example, this page 0 is loaded, the page 0 is loaded in the second frame, then it's a valid is currently being executed. It's a valid only. So page 1 is in the third one. It's a valid one. It's currently we are executing that one. Then page 2 is here. Page 2 is in 4. It's a valid. So like that all these pages we are executing currently with this till 5, it's valid, and there is no 6th and 7th pages. It's not yet loaded. It's not currently used by the CPU. Now this is denoted by this invalid bit. Then shared pages. The only copy of read-only code shared among the processes like text editors, compilers. Then similar to the multiple threads sharing the same process space. Then the private code and data, each process keeps separate copy of code and data. The page for the private code and data can appear anywhere in the logical address space. Here, for example, the shared data are ED1, ED2, ED3 or shared one. It's shared by process P1, P3 and P2. Here the data 1, data 2, data 3 are its own content. Now where it's available, the page table for this one is it's available in the 3. So the ED2 is available 3 and 4 and 6. C3 we have this ED1 and 4 we have this ED2, then 6 we have this ED3. Okay, so same thing for this ED. So it's a shared data, right? So 3 this sorry this 3 4, so common page table contains the common location only. It differs with the data 1, data 2 and data 3. It's not shared one. Then structure of page table. The memory structure for paging can get huge using straightforward methods. Can store 32-bit logical address space on modern computers. The page size may be a 4 KB. It's about 2 par 12 bytes. Then page table would have 1 million entries like 2 par 32 or 2 par 12. Each entry is 4 bytes. So 4 MB of physical address space. So memory for page tables alone. The amount of memory used to cost a lot. So we should not waste to allocate the continuous in the main memory. You can go for this methods like hierarchical paging or hashed page tables and inverted page tables. Hierarchical page tables, it's break the logical address into multiple page tables. Simple technique for two-level page table. See a two level, instead of having a single, you can have this outer page table and inner page table. There are two levels. Okay, in the outer page table that denotes where it's available in that actual page table. From that you can access the frame number. The two level paging example, a logical address is divided into a page number consisting of 22 bits and offset consisting of 10 bits, totally 32 bit. Then page table is page, the page number is further divided into 12-bit page number and this 10-bit, 32, 22-bit number. So here, if this is the address, what happened? This 10-bit is, this offset is, the offset of 10 is common. Okay, then the 12, the 22 bits are divided into page number with that. 22 bits divided into that two levels, the page table 1, page table 2. This go and refer the page table 1 for getting that page table 2, and there you have the frame number and add with that displacement to get that physical address. This is called forward mapped page table. So here page 1 for referring that outer page table, get that page table number, the page table inner page table number, then get the frame number here, then frame will be the added with that displacement to generate the physical address. Then 64-bit logical address. There are two levels of paging scheme. It's not sufficient. So we have to go for pages with 4 KB. The page table has 2050, so 2 par 52 entries. Such case, then how do you go? The if two level inner page table could be 2 par 10 and address this will be like 42 for this outer and 10 for inner. Okay. So if we increase, little tough to proceed with that. So we have to go for 3-level paging. The 3-level paging we have this. Again, this is about 42 instead of 42. 64 bits are there, right? So 64 bits here, you can divide into 3 levels. The inner level P1 contains the information about P2. Again, P2 is having the P3 and P3 has a frame number to add with that. So when the memory sizes increases, we have to go for different levels of paging. Next method is about hashed page tables. These are different ways to implement the page table. Here the common address space is 32-bit. The virtual number is hashed into a page table. The page table contains a chain of elements hashing to the same location. The virtual number, virtual page number, the value of the mapped frame are pointed to the next element. Okay, the virtual page number are compared in that chain searching for matching. If match is found, the corresponding physical frame is extracted. If it is increased to 64 addresses, then it's a clustered page table. So this hashed, similarly hashed, but entry refers to several pages, especially useful for sparse address spaces. Here we have a page table. This is a logical address. Okay, page number with that displacement. Apply the hash function, get this hash table, and here you have this different multiple queues to generate this where the actual value is available. It's a Q and S, then page and R. Take this frame number, add to generate the physical address. Inverted page table. Here, rather than each process having a page table and keeping track of all possible logical pages, track all physical pages. One entry for each real page of memory. Each entry consists of virtual address of page stored in the real memory location with information about the process that wants the page. It decreases memory needed to store each page table but increases the time needed to search that table when page reference occurs. So we have to use the hash table to limit the search to one or at most a few page table entries. So TLB can accelerate access. So one mapping of virtual address to the shared physical address is required for shared memory. Here, inverted page table, CPU generates the logical address. It consists of PID and page number and displacement. This PID, you are going to give the starting address of the page table and where you are going to find that page number, then get the frame number. It's like a displacement. Then get this I and add with the displacement, inverted number. Then the um, physical address is generated. So here these are the various way to implement the page table. Okay, the 2-level or 3-level scheme we can use, or the hashing method we can use, or this inverted page table. So we need page table for translating the logical address into physical address. Okay, then we can go for solving that internal fragmentation, external fragmentation. With the paging table is very important. Thank you.